All right, nice. Can I start? Is this okay? All right. I actually had your faces minimized, so I'm taking the silence as a yes, but okay. Um, okay, so hello again. Welcome to the VW Star lecture of the day. And today is going to be, I think, fairly short because I just have this one theorem to tell you about. Um, I think I realized last time I didn't introduce myself, but you can see my name in all caps. That is not how I say it out loud. Usually I say it in a normal voice volume. I don't scream Benjamin, but yes, you can just call me Ben if you have any questions. As usual, please just shout it out. Let's just get right into it. So I'm going to sketch to you a sort of technical issue that comes up when constructing von Neumann algebras. Which is maybe an issue that you're not aware of. So this is kind of that thing where I'm telling you that there's a problem, and then I tell you how to fix it. And you're like, well, I didn't know there was a problem there in the first place. So when you build a Von Neumann algebra, right? And I think I looked in the schedule, and I think this is one of the first lectures that you saw. How does it really work? Well, you take some kind of star algebra on bounded operators, and you take the bicommutant of this star algebra, or if you like, the strong operator topology closure. And the definition of closure in just general topological spaces means that every element in your von Neumann algebra can be approximated by nets in the star algebra, right? In the strong operator topology. Every x in the strong operator topology closure is the limit of some net of elements in the star algebra. Um, and to tell you the truth, when I was learning this, and for a long time after, I guess. In my mind, there was not really a big difference between nets and sequences. And tell you the truth, in many respects, there isn't. Uh, the way that I think about nets intuitively is that they're just sort of like sequences. But there are some pitfalls that occur when you use this kind of reasoning. Um, so why do we need nets in the first place? Why can't I just say that every x in the strong upper topology closure is the limit of some sequence of elements in A? I don't know actually how much the prerequisite notes go into this stuff. But let me just say, okay, do I have to do nets? Can I do sequences instead? Well, the problem is that the definition of convergence and continuity and this kind of stuff relies on nets in the most general setting. But when you learn about this stuff in metric spaces and real analysis, you have the benefit of working in first countable topological spaces, right? So this means that first countable in a topological space means that every point in your topological space um, has a countable base, right? So every open set is some countable union or some union of elements of your base, which you can take to be countable. And metric spaces are in particular first countable, but some topologies, like the strong operator topology, is not a first countable. Sorry, B of H with the strong operator topology is not a first countable topological space for infinite dimensional Hilbert spaces, which is where all the interesting examples for Riemann algebras come from, of course. This is some sort of fact that you can see. I linked the sort of Stack Exchange post that I looked at when I was researching this lecture. Last time I didn't highlight the links in different colors, and I decided to do this because it seemed kind of strange. Um, but what's interesting, of course, is that on bounded subsets, right, these operator topologies are metrizable, as we know. Um, and as I said, metric spaces are first countable. So if you restrict to some kind of closed ball inside of B of H, you don't have this problem. But in general, the Neumann algebra obviously is not going to be sitting inside of some ball in B of H. So even though you have some really nice properties of the topology, it doesn't give you this first countability. And if you don't have first countability, then you cannot use sequences in general, right? It's the same kind of, I'm not going to explain in detail why that is, but of course, if you have a countable base, you can extract out of a net some kind of sequence by using the countable base around your point that you're converging to. But if you don't have this luxury, then you can't do this, and you're stuck with nets. Um, Another example, just to tie it into the last lecture, this is the only time that I'm going to really reference the pre-dual. Uh, if your Neumann algebra has a pre-dual which is really large, so it has uncountable dimension, and this comes back to the question of separable pre-dual that was raised at the end of last lecture. But in any case, if you have uncountable dimension in your pre-dual, then this weak star topology, which we found agreed with the sigma weak operator topology on M, is also not first countable. So if you want, in general, a strong operator topology convergence type statement, you have to use nets and not sequences. And similarly, in some cases, okay, I don't know how often this would actually occur, but this is mathematics. I suppose you can't just say that. Um, if you want to use sigma weak operator topology convergence, you have to make some kind of assumption about the pre-dual um, in order to avoid working with nets. Okay, so this slide sort of shows you the necessity of nets. The question is, okay, I know that I have to use nets, but what's the issue with that? Again, if it's just kind of the same as sequences, well, there are some big differences, and this is the one that I'm going to focus on, which is that if you have a convergent sequence, of course, that's bounded in any kind of norm space. Um, but a convergent net doesn't have to be bounded, and this comes from basically the difference of the definition of convergence for nets, right? Nets are um, more flexible, much more flexible, but that flexibility comes at a cost. So here's one example, which is kind of a silly example, where I take these functions, e to the lambda x. Um, the net is indexed by lambda, and those are real numbers. And x is supposed to be the argument of this function, which is a real number between 0 and 1. And so the way that I constructed this example, let's see what did I want to say. So as lambda goes to minus infinity, right, this net of continuous functions converges pointwise, let's say, to 0, right? However, as lambda goes to positive infinity, the, there is no boundedness, right? These functions, for example, plug in x equals 1, and it goes to infinity. Um, okay, so that's a silly example because I'm only interested in the convergence to minus infinity in this instance. So the positive infinity unboundedness is not relevant. Uh, and unfortunately, this is the best example that I can give you explicitly because I don't know if you've talked about ultrafilters yet. I don't think so because I don't remember if this comes up in goals or if it's just kind of a thing that we mentioned on the side. Um, but if you have sort of ultrafilters in your toolkit, you can find nets which are convergent, but are not eventually bounded in the sense that you would think that they ought to be, right? So that you can say that, okay, if it converges to some point, this net, then there is some point after which it's still bounded. But I can't give you an explicit example of this at the moment, unfortunately. And just to tie this back to the pre-dual business, one nice thing about, for instance, this weak star topology is that the Banach-Steinhaus theorem, or the uniform boundedness principle, if you like, says that weak star convergence sequences are indeed norm bounded in the dual space of a Banach space. But again, this fails if you use nets. Again, the example comes from having ultrafilters. So somehow, if you sort of use ultrafilters are sort of generalizations of sequences in a different sort of sense than nets. So somehow when you drop the countability, things start going haywire. So the point of these two slides was just to say that you have to use nets, um, and you can't just get away with using sequences. But when you're forced to use nets, you lose some nice properties of sequences. In particular, you lose norm boundedness in general. And so you might begin to worry, what is the sort of salve for this, and that's what the Kaplansky density theorem addresses. Okay, so it's pretty much the exact statement that we would want after I laid out what the problem is. So again, you start with the sum star subalgebra. Oh, it doesn't have to be unital. I'll fix that. So you just take some star subalgebra and B of H. Unital is not necessary. And you take its strong upper topology closure. In other words, you take a von Neumann algebra generated by some star subalgebra. Um, the strong operator topology closure of the unit ball of A, unit ball in the sense of operator norm less than or equal to 1, is going to be the same as the unit ball of the completion. So if you like, the parentheses subscript 1 and the overline SOT, these two symbols commute with each other. You can take the strong upright topology closure first and look at its unit ball. That's the right-hand side. That's going to be the same as taking the unit ball first of A and then closing that in the strong upright topology. More than that, the same thing is true for the self-adjoint parts of the star algebra and the Neumann algebra, respectively. So, which is to say the following: if you have an element of norm at most one and you have a Neumann algebra, um, which is again the limit of some net inside of A in a strong upper topology, you can actually choose that net to be bounded and bounded by the norm of your original element. Let's see, point in the chat. Oh. Thank you. Thank you. Um, I guess I didn't I didn't read the notes close enough. There's so what Michael said is that there's an example in the goals notes of a convergent net which is not bounded. Thank you. Right. So this is basically a solution, complete solution to the issue that I posed. So I guess that's a rhetorical sleight of hand that I did. But anyway, it's nice. Um, okay, any questions about the statement of the theorem? If not, let me go ahead and so basically today I'm just going to prove this theorem to you, and that's going to be our lecture. There is a proof in the goals notes, which I did skim. I learned the proof from Popa's book, which is freely available online. It is different from the goals proof, and so I decided to give that proof so that you can see two different avenues of approach if you're so inclined. And so what's the idea? Well, so let me just go back one slide. So what you want is, of course, this is an approximation argument, right? So you have some kind of approximation of your element in the closure, and you want to do it by a bounded net. And so, I mean, if you think about sort of the general flavor of approximation proofs in analysis, you usually take some nice class of functions and use some kind of density. And similarly, in our case, we would like to use some kind of flexibility that comes from something like the continuous functional calculus, for instance. Because if you have a star algebra in B of H, I don't know what the analytic content of this star algebra is. So I'm going to restrict my attention first to self-adjoint elements so that I can use the functional calculus. And the functional calculus is going to help us in finding this bounded net. But there's, of course, a problem with this approach. As I said, I don't know anything about this A other than that it's a star algebra inside of B of H. So if I take a self-adjoint element in A and apply a continuous function to it, well, that's a norm limit of elements in A. But I'm not assuming that A is norm closed, right? But if I'm allowed to go back just one more time to the statement of the theorem, notice that what we're trying to do is we're trying to compare strong upper topology closures. And these are bigger than the norm closures, right? Because the norm topology is finer than the strong operator topology. So I can just start out and assume that A is a norm closed star subalgebra of B of H, right? Because if I take the strong operator topology closure of that, so let me say it this way. If I take A and then I take its strong operator topology closure, that's the same thing as taking A, first its norm closure, and then the strong operator topology closure of that. Okay. So I'm going to start by assuming that A is norm closed so that I have access to the continuous functional calculus. And now I just go along and I follow my notes. So I have an element in the strong operator topology closure. I start by assuming it's self-adjoint. And of course, I'm just going to scale it so that it has norm less than or equal to 1 just for simplicity. So it's in the unit ball. And of course, by definition, I get a net. I can take the, um, well, okay, so let me say this a little bit more carefully. This is something to check. It's not necessarily immediately obvious, but if M is a strong upper topology closure of A, the self-adjoint part of M is going to be the strong operator topology closure of the self-adjoint part of A already. Okay. Which is just to say that if I have a self-adjoint element in M and I know that it's a limit of some net of elements in A, I can just, by fiddling around with the net, I can assume that that net was already consisting of self-adjoint elements in the first place. Okay, so I just have self-adjoint elements converging to X in the strong operator topology. And I want to use a continuous functional calculus, and I'm going to pick a specific function, and it looks sort of unmotivated, and I'll explain what I want this function to do, and then, then maybe it'll be a little bit clearer. So I am looking at this element X, which has norm at most 1, and it's self-adjoint. So the spectral radius formula will tell me that its spectrum lies inside the interval -1 to 1, right? So what I want to do is I want to take a net which converges, and it's in general maybe unbounded. But so I'm going to take a function which is going to take all of R, right? So I'm going to take all of the spectrum of some self-adjoint element, and I'm going to squeeze it into the unit interval -1, 1, and this is that boundedness that I want, right? So, I mean, I'm sure that you see this now very frequently, but I just want to emphasize the use of this functional calculus is for instance, like this, right? That you can sort of squish elements and make them bounded or cut them off at some threshold. I guess for that you need some sort of more flexible functional calculus and not just continuous ones in general. But anyway, basically I just need a function which maps all of R into this interval -1 to 1. And I want its restriction onto the interval -1 to 1 to be invertible. So here is one such function, which is 2t over 1 plus t squared. As you can see, it is a bijection of -1, 1. But if I consider its domain to be all of R, then of course it's no longer injective. But the black and the red lines are meant to indicate that, in fact, it is bounded between -1 and 1 for all values of t. Okay, so this is going to be my continuous functional calculus. And what's the point? Again, the point is that it's a bijection when restricted to -1, 1. And so this last line is what I want to draw your attention to. So you can write your element X as f of g of X, g being the inverse of f when it's restricted to -1, 1. Of course, I might not be able to write such a statement if if X had a spectrum outside of -1, 1, but that's not a big assumption to make because of, again, spectral radius. Okay, so sort of any continuous function that maps R to -1, 1 and is a bijection restricted to -1, 1 would work. But I guess this one is also nice because it's sort of has a nice expression, a nice formula which you can manipulate algebraically. So I'm going to start by I'm going to give things names. So I'm going to set my element y, I'm going to call that g of x. This is self-adjoint because g is a real valued function and x is self-adjoint. And of course, x is f of g of x, so x is f of y. And y is again in the strong operator topology closure of the self-adjoint part of A, from what I said before. So by definition, I have a net in the self-adjoint part of A, which converges to y in the strong operator topology. And so what I'm going to do is I'm going to apply f to this. I'm going to apply f to this net. And notice that because of how I constructed f, because it's bounded between -1 and 1 as a real valued function, um, each of the f of yj's are going to actually be norm bounded and normed by at most 1. Okay, and if I have the desired convergence, right? So f of y I, okay, I should have, that's supposed to be a j there, sorry. So if f of yi converging to f of y in SOT, this will sort of finish the theorem for the self-adjoint case, right? So again, this f, the role of it is just to get the boundedness. So now I'm not going to go through this entire thing in the algebraic sense, but let me just say, so whenever you have to prove this by hand, right, that you have some kind of continuity or convergence, what I typically do, and this, I don't think I've seen this very recently in the sort of works that I've read for research purposes, but when you're doing the constructions for C-star and Riemann algebras, you sometimes run into these things where you do some kind of seemingly unmotivated algebraic manipulation, and I guess this sort of like a particular sort of phenomenon in the trade, right? That sometimes somebody just figured out the algebra and it works, so we might as well just take it and use it. So I'm going to use just the following expansion for f of t minus f of s, and now t and s are real numbers, so I'm looking at f as a real valued function. And so you just take common denominators, okay, move along this algebra, don't worry about this. And I'm writing sort of suggestively the last part. So what you get is 1 plus t squared and 1 plus s squared in the denominator. And then the difference between t minus s in the numerator shows up in two different ways. So this is how you would show in, for instance, in real analysis class, that this function is continuous, right? Because now you can do an epsilon delta proof on the distance between t minus s. And that's the same thing that you do on the level of operators, only of course the multiplication is no longer commutative. Um, so I put the 1 plus t squared and 1 plus s squared in the denominator here. But of course, the 1 plus s squared is on the right when you start. So when you're doing this manipulation on the level of operators, you just take what you saw in the real number case and you do it again, but you pay attention to the order of the products. But so that is to say that this 1 plus s squared would really go on the right of the entire product. And I want to just draw your attention to the fact that I have this t minus s here, and then a t minus s multiplied by t on the left and s on the right. And so when I do this on the level of operators, what do I get? Well, again, I have the sort of t minus s in the first instance, this yj minus y. And I have the 1 plus t squared in the denominator and the 1 plus s squared. Again, that goes on the right. That's the first term. And the second term is the same. And I made a typo here. So I think there should be it should be yj times y minus yj times y. So that's that t times t minus s times s or something like this on the right hand side. Apologies about that, but um, okay. So this is just the algebra for expanding f. And so some nice things happen now. So you know that the norms of the following operators are at most 1. 1 plus yj squared inverse, and also 1 plus yj squared inverse yj. And I'll let you just do this calculation yourself. You can check that the norms of these are at most 1. And so again, we're looking for a strong upper topology convergence. So what's nice is that on the right, I have this 1 plus y squared and y is fixed, right? I don't know what yj does. That again is a net converging to y that doesn't have any natural boundedness properties, but y is just a fixed element. So I'm okay with y being on the right. Or sort of the first thing that I do in this product. So if you plug this into this formula and use these bounds, what you get is yj minus y in both of the terms, and then some expression involving xi, your chosen element xi, and your operator y. But you know by assumption that yj converges to y in the strong operator topology. So whatever you have on whatever input you're giving yj and y, that's just some fixed vector in in the Hilbert space H, right? And I think this is where the typo is coming in somewhere. So, right, this yj here. Okay, so my apologies. Let me just make that very clear what the issue is. So it should be in the first line, this f of yj minus fy. The first term is correct, and the second term should be a uh, hmm, it maybe should be y times y minus yj times yj. So I'll fix that when I post the notes. Um, so in the end, when you do the norm manipulations, you get a y minus yj and then a yj. This does stay here. And so now there's just one more thing that you have to do. The first term is fine. Again, this is a fixed vector, and strong operator topology convergence takes care of this first term for bounding. The second term, you have to argue that because yj minus y converges to 0 in strong operator topology, that you have this for this product here. So now that I'm looking at it, there might be some typo here. So let me just check this. And then once that is done, I'll upload the corrected notes. But modulo this mistake here, the point is you get a bound which works in both cases is yj minus y and then some fixed vector or something bounded. So this does fill in the strong hypertopology convergence. So apologies for the typo here, but apart from that, it's basically just picking a nice function and then doing the algebra out. Okay. So what you have here then is you have for self-adjoint elements a proof of this theorem, right? So I know that every self-adjoint element can be approximated this way. If you don't have a self-adjoint element, you can't jump into the continuous functional calculus right away. And so there are multiple ways around that, right? What I decided to do and so I guess I should say what this proof decides to do is something that I thought would be kind of nice to include because it's an instance of the 2 by 2 matrix trick or the n by n matrix trick, which you saw in the proof of the bicommutant theorem, for example. So here what you do is you pass to 2 by 2 matrices with entries in A. And the inclusions are as follows. So that is going to be a subset of 2 by 2 matrices with entries in M, your mononomial algebra, your closure. And you think of that as 2 by 2 matrices with entries in B of H in particular, which is nothing but bounded operators on H plus H. Okay? And so I'm going to pass to the 2 by 2 matrices. So I just need to record that the strong upper topology convergence on this larger space, this bounded operators on H plus H, it's the same as entry-wise strong upper topology convergence on matrices, 2 by 2 matrices in B of H. Okay. So if I want to know that a net converges an SOT on the former space, I look at the 2 by 2 matrix and I just look at each entry and I need each entry to converge in SOT in B of H. Okay. So this is what you always do, right? So if you have an element in M which is norm-bounded but not self-adjoint, you construct this 2 by 2 matrix where you just put X and X star on the off-diagonal parts. Okay, and so you check that X is, well, check, okay, you look at it and you see that X, capital X, is a self-adjoint element um, in 2 by 2 matrices with entries in M, and its operator norm as a matrix, 2 by 2 matrix, is indeed less than 1. Okay. Okay, so you apply the first part. You have a self-adjoint element norm bounded at most 1, so you get a net in the self-adjoint part of M2A, which converges to X in the strong operator topology on B of H plus H, which I call Yi. And by the first part, you can assume that Yi has norm at most 1, operator norm at most 1. And so you see, if you look at the top right entry of this matrix, that you have this Bi which converges to X. And because the strong upper topology convergence again is the entry-wise convergence, you get that Bi converges to X in the SOT on B of H, not B of H plus H. And again, by doing a little bit of type checking, messing around maybe with the formula, you can see that you can choose or rather assume that Bi is actually self-adjoint. It's not necessarily obvious from the fact that Yi is self-adjoint, but you can assume that Bi is self-adjoint. And because Bi is just one entry in this matrix Yi, in fact, the norm of Bi, I think is something like this, right? So you can check that because you assume that Yi has norm at most 1, you follow that Bi um, has norm at most 1. I think if Bi had a norm bigger than 1, maybe you could find some vector which contradict the operator norm on Yi, or something like this. Okay, so the non-self-adjoint case is handled by going to the 2 by 2 matrices, is I guess the point of this entire thing. And this I thought was just a cute application of this trick again. Um, okay, so I know that there was some mistake I made in the last line of the previous slide, so I'll fix that. Apologies, but are there any questions about this last part of the proof? You can take home the 2 by 2 matrix part as a sort of nice application of the trick, but the point is you don't need to particularly remember crucial details about the proof. The point is just that it's sort of a foundational sort of theorem. It's kind of the same thing as like, I don't know, like Lucin's theorem or Egorov's theorem or something in real analysis, which is a thing that you could, give to you could put on a qualifying exam if you feel particularly evil or something like this, right? But it's a type of theorem that you use uh, all over the place when you're sorting out foundational issues in the theory. It's not necessarily something that is a particular tool for a particular purpose. Okay, so now that's the theorem. That's all I want to say about that. And I just want to close by giving you some um, corollaries, some applications of the theorem. And again, these are going to be of the flavor of sort of foundational type statements. So here's a long list of equivalences, for instance, on when you know that a star algebra in B of H is already a von Neumann algebra. So if you have a star algebra in B of H, it's a von Neumann algebra if and only if the following things are uh, are satisfied, right? So the unit ball is weak operator topology closed or strong operator topology closed. I can say that 10 times fast, or sigma weak, sigma strong. Right? Okay, so let's see how this proof goes. Well, if A is a von Neumann algebra, right? Here's one way you can argue, right? So if A is a von Neumann algebra, for instance, you look at its unit ball, that is going to be uh, the unit ball of B of H intersected with A, right? And on the other hand, A is a dual space, right? If it's a von Neumann algebra, it has a pre-dual. So its unit ball is actually compact in the sigma weak operator topology by Banach-Arnauld, right? And in particular, compact sets are closed. Now, the sigma weak and the weak operator topology are the same on bounded subsets. So this will tell you that, in fact, the unit ball of A is weak operator topology compact, right? But that's equivalent to it being closed because it is the sort of because it's the closed intersection of the compact set in B of H, unit ball B of H, unit ball of B of H in the weak operator topology, um, and so forth. I have this written out, but I want to see how well I could remember what I wrote down. Not very well, I guess. Um, right. So again, this is the point. So if A is a von Neumann algebra, then the unit ball is sigma weakly compact, which is the same as weak operator topology compact. On the other hand, if unit ball is weak operator topology closed, but this is what I want to say. Well, closedness and compactness are equivalent in this instance, right? Because if your set is weak operator topology closed, it's a closed subset of the weak operator topology compact set, which is B of H sub 1, right? So it's automatically compact. But why do you need the Kaplansky density theorem for this at all? So if A1, if unit ball of A is weak operator topology closed, you want to show from that you can conclude that A itself is closed in the weak operator topology. Well, you take an element of norm at most one, you apply the Kaplansky density theorem, which works in the weak operator topology as well as the strong operator topology, right? Because um, the WOT and SOT closures of convex subsets of B of H will agree. You take the Kaplansky density theorem, and the point is that you can find this net, which is actually in the unit ball of A, right? Um, and since the unit ball of A is WOT closed, um, you find that X was actually in the unit ball of A to begin with, right? So you go from having X in the closure of A to having X actually in A. So therefore, you get that A is WOT closed, so it's a Neumann algebra. And then you do the same kind of reasoning for the other um, statements, right? Okay, so I guess the nice thing about this, I don't know if you would frequently run into a star algebra in B of H where you happen to know that its unit ball is sigma weakly closed, and you have to conclude from that that it's a Neumann algebra. So I guess the implications are more interesting when you start from saying, okay, A is a Neumann algebra, and then you go in the other direction. But I'm sure that there are examples where the other implications are useful as well. And then just the last thing that I wanted to say is this thing, which is in the goals notes. I'm sorry, I forgot to notate which theorem or something it is. But if you have a star subalgebra of B of H, this now tells you that there are, I guess, one, two, three, four, five different ways that you could find or describe rather the von Neumann algebra that A generates. You could take the sigma strong closure, the sigma weak closure, the strong operator topology closure, or the WOT closure, or the bicomutant, then these things will all give you the same exact thing. And again, some of these things follow just by comparing the topologies, right? So if right, so the strong operator topology closure will be containing now how does it go? The strong operator topology closure will be contained in the weak one, for instance, right? So if you have a net which converges in the strong operator topology, then it also converges in the weak operator topology, something like this. But the point is just this. If I have a net which converges in SOT, then by this theorem, I can assume that it's a bounded net, right? So this allows me to say that if I have something in the SOT closure, it's actually also in the sigma SOT closure, right? Because the SOT and the sigma SOT agree on bounded subsets. And so you take these statements and you sort of shuffle them in with the comparisons of the topologies. Okay. Right. So I suppose that's all that I had to say about this. This is sort of a um, shorter section. And I encourage you, though, to read the proof in the goals notes, which is different, which uses functional calculus in a different way. Um, and I think it's nice to compare these two. I don't think that proof uses the matrix trick. So I think it's nice to see these two things, sort of understand how these things fit together. But okay, I'm going to stop there because this is the end of my slides. So thank you. I will correct the mistakes. I'll put it just as with the last lecture notes, I'll put it on the goals Discord, and I will also upload this. So let me stop the recording and then see if you guys have questions.